Everybody knows wastewater is a challenge. We don't treat enough of it, right? Depending on which paper you read, anywhere from 20 to 50% is what we treat in terms of global volumes. So that means anywhere from 80 to 50% it remains untreated. So, or minimally treated, right? And this is our agricultural runoff, this is our industrial discharge, this is our sewage. So we have a significant volume that we still have to address. But given the percentage of wastewater that we do treat conventionally, right, with the existing infrastructure that we have, requires a massive amount of energy, especially if we're talking about aerobic digestion, highly skilled operators, and a very significant infrastructure investment to treat the percentage of wastewaters that we do. And the industrial sector, right, you have very highly concentrated waste, and this becomes a pretty big challenge, especially if you're a large producer in a small municipality. And so if you read the latest and greatest, right, treating what we treat the way that we do it now generates more greenhouse gas emissions than the shipping industry. This is a massive amount of emissions. And there was a study that was published from Princeton University in February of this year that showed measurements of 63 different utilities, specifically the anaerobic digesters across the United States. And what they found, comparing their data relative to measurements done by the EPA and IPCC, that there is a significant underestimate relative to the emissions that our industry produces daily. In fact, about a factor of 2. And so we've got some significant strides that we need to make. Now, most of these emissions are actually coming from leaky anaerobic digesters. So anaerobic digestion is often seen as a wonderful technology, and it's the industry standard for dealing with high-strength wastewaters. And you can do energy recovery, right? You process that high-strength waste, you generate some methane, you can purify it for a cogeneration process, or you can inject your natural gas. It's a great solution. But unless you've got an airtight chamber, you've got some significant emissions that were not previously accounted for. So probably our baseline in terms of what we are at in terms of industry is much higher than initially anticipated. So we got some work to do. So now how do we do it, right? A majority of our wastewater is captured. About 63% is captured. 20 to 50% is adequately treated before discharged. If you look at the amount of consumption globally and per water usage, this is a proxy for how much wastewater we're discharging as well in terms of overall percentage. So municipal water, right, we're utilizing 10 to 12% of our global water demand. Industrial is closer to 20%. And of course, most of our consumption and runoff is associated with agricultural processes. I'm going to focus on the industrial sector, and this is where Aquacycl plays a role. It's a pretty big segment relative to water that we need to treat, and it is some of the most challenging wastewaters out there, very high strength, high concentration. So Aquacycl, what we do is a bioelectrochemical treatment technology. It is energy recovery is possible, although that's not really a part of our value proposition. We can complement anaerobic digestion processes, but we work at a scale that's a little bit higher. So our incoming concentrations are anywhere from 50,000 to 150,000 parts per million of biological oxygen demand. So we're so far the only technology on the market that can treat undiluted wastewaters from food and beverage processing. So that means any given production process, most of the wastewater is generated from cleaning. So let's say a bottling facility, for example. You're going to be potentially manufacturing the syrup that goes into a can of soda. 1/5 of that can is the syrup, 4/5 is sparkling water. If there's a bad batch of that syrup, you have a few thousand gallons of very concentrated wastewater that goes down the drain. That becomes a big challenge for a municipality. Say you have expired product that's coming back, and anything that's damaged or expired through the distribution system or in the bottling process. Manufacturer wants to recover the aluminum and the plastic. They crush all of that product, the cans and the bottles, and they do that material recovery, but all of that product now goes down the drain. Now these BODs are extremely high, and so most of municipalities count on a good amount of dilution in order to be able to deal with this stuff as it comes down the sewer. However, as bottlers are actually reducing their water consumption, that means less dilution factor. That means a pretty big problem for the municipality and for the producer. So that's why we look at these undiluted streams. That's why we play in a space that's a little bit above where digesters are, because we can treat these very specific small volume, high concentrate streams, so the majority of the water that leaves the plant, fairly high quality, to enable reuse and to also enable a little bit more liability and open capacity for the municipality. So when you compare our technology relative to activated sludge, conventional process for aeration, anaerobic digestion, and this is not high rate anaerobic digestion, this is your conventional process, and us, the bioelectrochemical treatment technology, or BET. There's a few things that we're addressing in the carbon cycle. So number one, if we go apples to apples comparison in terms of the amount of BOD, COD that we remove on a daily basis, we produce a lot less biomass. So this is a lot less wasted sludge that ultimately has to be collected, trucked, and otherwise managed. And by managed, typically that's sending to a landfill where it then breaks down into greenhouse gases. So minimizing the volumes is a big help, right, in that carbon cycle. But the majority of the savings in terms of greenhouse gas emissions comes from saving energy. So if we look at the amount of energy that is required for treatment, again, apples to apples comparison, looking at an activated sludge process requires a pretty significant energy demand. Estimations are anywhere from 0.5, 1.2 kilowatt hours per kilogram COD that's required from an aeration technology to treat these concentrated streams. Now, it can be as high as 2, right, if you don't have good mixing, etc. With anaerobic digestion, it's lower. You cover a little bit of energy. With our system, we're actually 2 orders of magnitude lower in terms of energy consumption. So you're looking at 0.02 to 0.04 kilowatt hours a day per kilogram of COD that we treat. Can be in the same range of energy recovery, but what we make is actually DC power. There's no biogas that's generated out of our system. There's no methane. So as DC power, if you wanted to convert that to useful energy, right, you'd have to do a DC to AC conversion. There's a lot of losses. We try to avoid that. But when we're on site, we're either trying to power ourselves or forklift charging stations, LED lighting for a warehouse, etc. So we don't have the loss associated with that conversion. Where we fit into the treatment cycle is a number of different places. So our bioelectrochemical treatment technology can sit and handle these really low volume, high concentration streams. In that case, we want to remove as much BOD, COD as possible. Then we're discharging to a post-treatment plant, right? So typically an aeration technology. Then we can go off into a membrane system for reuse. So it can be a part of a full solution to enable the customer to reuse water on site. I'll say a customer or a municipality already has anaerobic digestion. Now, we just talked about the fact that we're probably underestimating how well our digesters are working. But, say if we can keep them really working well, keep all of the gas trapped, energy recovery is a big deal, right? It's an important part of the anaerobic digestion process. But you lose a lot of energy if you have to separate your solids and landfill them. And often, the total suspended solid loading that's allowed in anaerobic digestion is quite low. But we can take that up to 10,000 parts per million of total suspended solids on consistent concentration to our systems. So if we're looking at higher volumes, we can utilize our system to break down total suspended solids, feed to an anaerobic digester, and actually increase biogas anywhere from 14 to 50%. So we're excited about the possibility of being able to plug and play and complement existing technologies. But I'm going to focus on one particular application today, and that's our work with Pepsi-Cola. In this case, it's volume, high concentration, that bottling example that I talked to you about before. So flow out of the facility anywhere from 100,000 to 150,000 gallons a day. But only about 3% of that flow represented 60% of their sewer bill. So these are the bad batches, this is the returned, expired, damaged product. And so we've been operational in their site in California here for about 2.5 years. Over that period of time, we've shown a net 30% reduction in their sewer bill because we're eliminating the surcharges and making sure everything is normalized without these major spikes of bad batch that might go down to the municipality. And because we're treating anywhere from 1,600 pounds to 3,000 pounds a day, load removal, only 60 kilowatt hours, we're actually mitigating over 100 tons of greenhouse gas emissions every single month, because the equivalent energy requirement at the activated sludge plant would be closer to 2,500 kilowatt hours. So the mitigation story is what enabled this relationship to become public. Before we weren't actually able to talk to the fact that we're working with Pepsi, even though we were saving them money and normalizing their sewer bill. But because there is such a focus for environmental, social, and governance goals, scope 1, 2, 3 emissions within enterprise clients and consumer product goods companies, this became an exciting topic for them to speak about as well as for us. So I'll tell you how it works. So we utilize the bioelectrochemical treatment technology, and it is very similar to a microbial fuel cell. We got it to work. We utilize naturally existing bacteria already present in wastewater or sourced locally in the environment that we're working in. So there's nothing that is genetically modified. There's nothing that's grown in the lab. We bring our containerized system to a customer site, source the material locally. We mix it with the wastewater that we're trying to treat. And the bacteria start to form biofilms, or fixed films, inside each one of these reactors. If you want to see what these reactors look like, we're over in booth B245. We've got one over there. So you can see what the inside and what the system physically looks like. So the bacteria attach, and they start using these surfaces as a way to breathe, or a way to respire. And in that process of respiration, the bacteria utilize that surface, which is a conductive anode, as a way to dump electrons. We capture those electrons, we move them across a circuit, and we generate DC power. Faster we move away those electrons from the bacteria, faster we're making them respire, faster we're making them breathe. And they're breathing really fast, they eat really fast. So the more electrical current that we draw, right, the faster we move electrons away from the bacteria, the faster the treatment rate. So essentially we are electronically controlling microbial metabolism. So stack these units together like Legos. Each one is about the size of a standard car battery. We pack them into a shipping container. We plug and play onto a customer site. Now, hydraulically, each box, it's not operating independently, right? We have 40 of these reactors that are operating in hydraulic series. The number of reactors we have in series defines how much BOD/COD we can remove from the incoming waste stream. And depending on what it is that we're treating, so with Pepsi, we're removing anywhere from 60 to 85% of whatever it is they're sending us. And that accounts for 1,600 to 3,000 pounds a day of total load. Now, we're only processing a small volume, right, but very high concentration. Each 40-foot container can process about 10,000 gallons a day, but if we have to go and address larger volumes, we would take the stacks of reactors outside of the container and basically rack them up, similar to how you would see a desalination plant. You put it in a warehouse, we've got lines of reactors that are consistently working. So the other advantage of the tech is that it is pretty simple. And because each one of these reactors is generating electricity, it's a signal on performance. And we have integrated sensors also, so we can know what's happening with flow, with pH, with COD and BOD removal. And all of that information is coming to us real time. So we know the health and performance of each system in the field. We can catch issues before they become real problems on site. Most of the time we can troubleshoot remotely without having to send an operator, which means we don't need a full-time operator on site at the customer site. Reduces our costs and it really simplifies the process. The things that break are the pumps. So if any of you make really good, reliable pumps, I'd like to talk to you. But we plug and play. Like I said, this particular model's been going for 2.5 years with Pepsi, very successfully. Within the bottling sector, we typically can show our customers a 20 to 60% saving against what they're doing. 100% compliance to whatever permit they're operating under, whether that's industrial discharge to sewer or NPDES to the environment. And a 90% reduction in greenhouse gas emissions relative to anything on the market today. So we've been validating the technology across a lot of different applications over the last 7 years. Brewing, so we deal with the trube, we deal with the really high concentrate stuff. In distilling, it's pot ale, possibly some spent lees as well. In confection, it's candy coating and some chocolate. And in hydrocarbon remediation, we can actually deal with aromatics and long chain hydrocarbons, moving them down to below detection limits. Same process, same approach. And our longest running system is actually at a pig farm, eating manure for the last 7 years. And this is really our longevity study. So over the last 7 years, we have not actually had to replace a single component on the core tech, replace pumps. We've opened up the boxes to see how they're doing. But overall, done some terrible things to these systems. We've let them dry out over several months. We've bleached them. We've run a lot of different chemical cleaning products through them. But because it's a biofilm system, because it's fixed film, it's extremely robust. And when we bring back into a consistent operational environment, we see recovery in 24 to 48 hours. Right back to the same levels in terms of BOD and COD removal and energy recovery. So we've also worked with the US military on demonstrating how this technology can retrofit into sanitation solutions and replacements to chemical toilets. That ultimately is our mission, sanitation for all. Because still in 2023, more people have a cell phone than a toilet. And so our goal is to be able to take these same little black boxes, retrofit them into different footprints to apply to rural and urban sanitation situations. So you have a technology that can work without an energy grid and without a sewer grid, providing safe and reliable sanitation. Ultimately, that is our goal. So I'm more than happy to answer any questions. We're based in Escondido, California. We've got offices in the Netherlands, expanding into the European market. And we're really excited for how this technology can apply and help decarbonize wastewater overall. Thanks.
Where's the Pepsi plant? And they give tours.
They do allow tours as long as you don't work for Coca-Cola. And it's located in Fresno, California.
I imagine that with sugar water, you don't have to worry about debris too much, but do you have other applications where you have to screen? Or?
Actually, we do have to worry about debris. So because of the crushing operation that's going on there, they're collapsing these bottles and cans, and so you get labels, you get caps, you get all kinds of stuff that can wind up in our reactors, and we have actually pulled a plastic bottle out once. But we do have a basket strainer as an initial straining process, and then we have Y strainers with varied mesh sizes in terms of moving contents between tanks and then into our system. And to deal with the stuff that we don't catch, we have maceration pumps. So we'll grind up soft matter before it feeds into our system. And depending on how soft it is and how much the loading is, we might do a solid separation step, either centrifugation or SAF. We can handle 10,000 parts per million of TSS. We've tested up to 35. We don't like it. We can do it, but we don't want that much. So we do try to separate out and then re-feed back into the system so we can translate that ultimately into energy.
harvesting electrons from organisms. These are the same organisms from the active sludge process. Where are these organisms that are?
So question was, how does the technology work? Okay.
Tell me what's in the box.
Yeah, what is in the box? Yeah, what is in the black box? So it is an anaerobic process, and what the black box does is it creates an environment that selects for organisms that have this capacity for electron transfer to solid surfaces. So in an anaerobic process in digestion, right, your anaerobic bugs are fixing CO2 to methane. That's what they're really good at. Our bugs don't make methane. And so what they naturally do in the environment is they are driving mineral cycles. So they live naturally in lagoons and sediments. They're even in your guts. They drive sulfur cycles and metal cycles. And so what they'll do in the environment in sediments is where we bioprospect, because they're going to live in a high diversity of different types of organisms as the minor population. So when we're going out to find the material, we're looking for really black, dense mud that stinks like rotten eggs. That's where our bugs live. And they're going to be at an interface where it's anaerobic and aerobic environment. So you're going to have minimal mixing, a little bit of oxygen, and then you're going to have an anaerobic interface. We want a huge diversity of organisms coming into the box initially. And then we're creating a selective pressure so that only those bugs that have that electron transfer capacity stick around and they outcompete the others. It takes about 1 month to establish that biofilm, and we're inducing different electrochemical parameters around the bugs to get them to solidify and stay in place to grow and be happy. And then we change from a batch condition into continuous flow. There's another equilibrium that has to happen. But it's a concert of organisms, right, doing hydrolysis, fermentation, ultimately fermentation byproduct into electricity. Anaerobic, but the completing reaction is on the cathode interface, which is a natural gas diffusion electrode, where we take the electrons across the circuit. Those react with the oxygen at that interface, not in the bulk, it's right on the surface. And we generate hydrogen peroxide, which helps to reduce biofouling at the surface, and new molecular water leaves. Yeah, so the oxygen, show this reactor scheme here again. So the white wall on the reactor is a gas diffusion electrode. So that means there's no forced air in the system, but oxygen can permeate across that white barrier. It's open to air. Yeah, so on either side of that box, we've got a gas diffusion electrode. So that's the side wall on each box. So oxygen is going to diffuse naturally through that membrane structure. And then the oxygen is going to react with the electrons coming across the circuit and the protons that are evolved from the oxidation reaction internally. And that evolves new molecular water and H2O2. That H2O2, the peroxide, reacts internally. It doesn't stick around. But the new molecular water leaves. And it's only a little bit. Come check out the box, 8245. Any other questions?
It's a high pressure situation inside the box? Or?
No, it's low pressure, 5 psi. Primarily, we're running gravity feed. So the pumps that transfer wastewater into our systems, they're actually not shown here. There's a lot of different feeder boxes that are associated with each plane of reactors inside the container. So the height of the feeder box relative to the plane of the reactors it's feeding is what defines the maximum flow rate for the system. So that's gravity fed in. We do have a transfer pump, but it's like 1/8 horsepower. It's pretty tiny. And then our maceration pumps, which help feed it into the supply tank. So the precision control on the back end of the treatment train is a peristaltic. So we can very precisely control the total flow rate. But it's the height of that feeder box that is maximum flow through the container, and that's gravity fed. Now, if we're not in a container, we can flow a lot faster because we hit the ceiling height, right? So in a warehouse situation, we can flow a lot faster, but it's still low pressure, 5 psi or less. So the question was BOD reduction. So we start on the high end, right? We're taking in 100,000 parts per million. We're going to remove anywhere from 85 to 99% of that.
During startup, do you have to provide like an initial charge
The question was startup. Do we need to provide a charge? No. So what we're doing is how we are controlling the electrochemistry in the system is, first off, we just want them to form a biofilm. So we're not stressing them out. So it's basically open circuit. So there's a minimum polarization between the anode and the cathode, so a really big resistor. And we're just kind of mixing in the wastewater and allowing them to settle on the surface. Then we step down the resistor. We start allowing more current to flow, and that puts more stress on the biofilm. And then over time, right, we're stressing them out to a point they can't keep so much energy growth. We keep them in a fixed maintenance mode. So we're not generating a lot of extra sludge. That's how we minimize our waste biomass. And so, but that's the month process. It's a very stepwise procedure. Build the biomass, stress the biomass, and then they do what we want them to do. Any other questions? All right, we're right on time. Thanks, guys.